All right, friends, welcome back. Happy Monday. Hope you had a good weekend. So, what we'll do in the first few minutes is try to summarize everything you've learned in terms of HOMO and LUMO and put it together. We've done that with a few examples. I feel like you could use a few more. Basically, in organic reactions, when the HOMO of a nucleophile attacks the LUMO of an electrophile, you get a new bond. And what happens next depends on the identity of the LUMO. If it's an empty p orbital, nothing else happens, you just get a new bond. If it's an antibonding orbital, not only do you form a new bond, but you have to break the old bond. And you've seen examples of this. For example, one of the ones that I think we probably did last week was this boron-containing molecule BH3, which is going to be our electrophile. At this stage, you don't need to worry yet about identifying the nucleophile versus the electrophile. We're going to give you some tools that will help with that. For now, it's useful to just look for clues. For example, in the problem set, when I give you these kinds of problems, I not only show you what the starting materials are, but I also show you what the products are. Yeah, it's recording, thanks. So if water is your nucleophile, what you care about is the HOMO on water, which should be the lone pairs on the oxygen. If BH3 is the electrophile, what you should care about is the LUMO on the electrophile, which in this case is what? Empty p orbital. Now that's been a popular question. How can I tell if there's an empty p orbital? There's basically two times you're going to find that in this class. One is on boron that's bonded to three things with a neutral formal charge. And the other time is a carbon that's bonded to three things with a positive formal charge. And the reasoning goes like this. You use the formal charge to determine that there is in fact no lone pair on boron or carbon. Both of these examples are basically the same situation, that the boron or carbon must be sp2 hybridized trigonal planar, and therefore you can account for each of the sigma bonds as coming from an sp2 orbital on carbon or boron, and so what's left over is a p orbital that's not involved in bonding. It doesn't have any lone pairs. It's still there, it's just empty. It doesn't have any electrons in it. It's a non-bonding orbital because it's not participating in any bond. And so it is necessarily higher in energy than any of the bonding orbitals and lower in energy than any of the anti-bonding orbitals. So it's a slam dunk for being your LUMO because it's lower in energy than any of the anti-bonding orbitals. So you predict HOMO attacks LUMO, draw an arrow from the HOMO of the nucleophile to the atom that the LUMO is on in the electrophile. And then because this is a non-bonding orbital, it's not involved in a bond, it's just an atomic orbital on one atom, you conclude that you're done. You've drawn the mechanism of this reaction. The arrow from HOMO to LUMO always signifies the formation of a new bond, in this case a sigma bond, and that bond is right there. And you need a negative formal charge on the boron as well. Okay, similarly you could do this with the carbocation below, and you would get basically a similar product. HOMO attacks LUMO, and when the LUMO is a non-bonding empty p orbital, then all that happens is you make a new sigma bond. Now, notice that the trigonal planar carbocation or boron species has this empty p orbital is sort of evenly distributed on both sides of the molecule. That's going to be important in a couple of chapters. One of the things you would predict is that the nucleophile should be able to attack that empty p orbital from either side. There's no difference from one side or the other. It's on either side of the molecule. That'll have some important consequences for reactivity and structures of products a little bit later on. Okay, questions about that? No, you are bored with that. Okay, I got more. Let's do a molecule with a pi bond in it to as your nucleophile. And then we'll use HCl as your electrophile. So remember, in the nucleophile, you care about the HOMO. In the electrophile, you care about the LUMO. What is the HOMO of this nucleophile? Pi bond. You can tell it's not non-bonding lone pairs because there aren't any. And you can tell it's not the sigma bonds because pi bonds are less stable than sigma bonds. Good. Carbon-carbon pi bond. If we were to draw that, it would look like this. That is the lobe of the orbital that's above the plane of the page. And then back behind the plane of the page, you've got the opposite wave function sign. Okay, now let's look at HCl. There's not that many bonds going on in HCl. So what is the LUMO of HCl? Boring. It can only be the hydrogen chlorine sigma star because that's the only empty orbital you've got in this molecule. If you were to draw the hydrogen chlorine sigma star, you could draw a node between the two nuclei, and the sigma star would look like this. You'd fill in color to indicate changes in wave function sign that would show you where the nodes are. Now, when the LUMO is on more than one atom, as it is here, and as it will be anytime it's an antibonding orbital, you have to decide which atom of the LUMO gets attacked. Your best bet is just to use your electronegativity intuition. Chlorine is more electronegative than hydrogen, so you expect chlorine to be electron rich, and you expect hydrogen to be electron poor, because chlorine's more electronegative, and the electrons in this hydrogen-chlorine bond are leaning away from hydrogen. So it should make sense that you should attack the empty orbital on the place of the molecule that's electron poor. And that'll generally be a trend that we use to decide which atom of a LUMO gets attacked. So now we draw an arrow. First commandment of OChem, HOMO attacks LUMO, nucleophile attacks electrophile. We decided to attack on the hydrogen. This arrow means we're forming a new sigma bond involving the hydrogen, but because this is an antibonding orbital, you need another arrow. You must break the sigma bond. And the electrons, once you've decided which atom gets attacked, the direction of that second arrow falls directly from that. You don't have to worry or wonder about that. The reason for that is if I pushed this arrow onto the hydrogen, I've gone and done what? I've broken the rule. There's too many electrons on that hydrogen, right? That hydrogen experiences these two electrons from the bond and these two? Right? So once you decide which atom of the LUMO to attack, the other atom gets the electrons from that bond. Yes?
Does it matter whether same phase attacks same phase versus opposite?
Yes. Does it matter whether same phase attacks same phase versus opposite phase? It probably does. I'm thinking that's a good question that I don't really know the answer to, other than you would work it out in high-level MO theory calculations. For our purposes, when at HOMO attacking LUMO, no. Okay. Others? I should have chose my colors briefly too, so that we wouldn't even have to worry about that, but that's okay. All right, others? Now, one question you got here, this is tricky, and you'll come up with this issue later on in the class. If you look at the HOMO of the nucleophile, that HOMO is also on more than one atom. So you now got another question, which of those two atoms gets the new sigma bond? Fortunately here, carbons 1 and 2 are identical, so we don't really care. But sometimes we will, and we'll have to decide which of those two atoms gets the new sigma bond, and there will be a principle for that we'll show you. For now, let's just say carbon 1 gets the new sigma bond. So this is the new CH bond involving carbon 1. Carbon 2 now, the electrons from the pi bond are now in the sigma bond with this new hydrogen, so what should be on carbon 2? Yeah, carbon 2 should have a positive formal charge. It basically lost 2 electrons. Now, sometimes reactions lead to products that are just done. Other times reactions lead to intermediates that can further react. What do you notice about the products of this reaction? You got another electron deficient molecule, another electrophile, and then you've got something that's got a negative charge on it. That's usually a good bet for a nucleophile. So, make a prediction. What do you think is going to happen? Chloro, I should draw the arrow where? To the empty p orbital that's on. That's an annoying line. I'm really annoyed by that. Yeah, you should attack the empty p orbital and make a new bond. What we've just done is a chapter 10 reaction, but you can see now why it makes sense. And both steps involve HOMO of the nucleophile, which in this case is lone pairs, attacking the LUMO of the electrophile, which in this case is the empty p orbital. Okay, so this is a powerful principle. It allows you to predict what would happen in an unfamiliar situation. I want to do just a couple more examples. Yeah, go ahead.
What do you call that last molecule? Is it in like nucleophile or electrophile now?
The product?
Yeah.
So that's an interesting question. This would be a decently stable product, but since you've been taught to look for stuff, if you had to pick a HOMO, what would it be? Yeah, the lone pairs on the chloro. Okay, now it hasn't got a negative charge, so maybe you're thinking, probably not that reactive. If you had to pick a LUMO, what would you pick here? Yeah, you would pick the carbon chlorine sigma star. And you will see that this molecule will be an electrophile because of the weakness of that carbon chlorine sigma star. So for example, I could, at this stage, introduce a nucleophile. So this would be, reaction 1. This would be reaction 2. Suppose I introduce this nucleophile, a negatively charged oxygen. You'd say, if you looked here, the HOMO should be the lone pair on oxygen. And you guys just identified the LUMO, which is the carbon chlorine sigma star. I could draw that 2 lobes towards the node that are small, large lobes pointing away from the node. This LUMO is on both carbon and chlorine. Which of the 2 atoms do you think gets attacked by the nucleophile, just based on electronegativity? Carbon. Good. So if we're going to attack on carbon, my arrow should go from here to here, and then what do I have to do? Got to break the bond between carbon and chlorine, and electrons go on the chlorine. And here is my new sigma bond that I just made. and then here is the chlorine that got kicked off. We have actually just done our first synthesis. In organic chemistry, we like to make molecules out of other molecules, and you can build one reaction on another to make new carbon-carbon bonds and put new electrophiles where they need to be. In this case, we started with an alkene. We have a carbocation that the chlorine attacks. We now have chlorine and a weak CCl bond, and we can bring in another nucleophile. If that's overwhelming to you, that is okay. We're not going to be doing synthesis for quite a while yet, but you're seeing how we can stitch multiple reactions together. The reaction I just showed you, this 2-reaction series where the alkene, erasing stuff, the alkene attacks the acid and then chloro attacks the carbocation. That 2-reaction series is called an addition reaction, because in the end, if you look at the products relative to the starting materials, I'll just highlight in purple the things we added relative to the alkene, right? The alkene used to not have 4 bonds to each of the carbons. We added a hydrogen on one side and then a chlorine on the other side, and that's an addition product. So the first reaction is an addition reaction. The second reaction is called a substitution reaction because we've swapped out this nucleophile for the chlorine on the carbon. We've traded them. Those are going to be 2 main reactivity patterns that you encounter in OChem. Other questions about that? Yeah.
I had a question about the MTP orbital example. Why would it be favorable to bond there even though it introduces charges?
Why would it be favorable to bond there even though it introduces charges? That's a great question, and it has a different answer depending on which of these situations you're looking at. This one is neutral, so it does introduce charge, but no overall charge change. This to this, also the charge stays the same. So actually, bond formation is always favorable. So probably these are downhill in energy. The other thing that can happen actually that we'll learn about is this oxygen-hydrogen bond is acidic, and a base could come along and remove it, and then the molecule would be neutral. So that can make it overall downhill. We'll have lots of examples of that in the future. Others, yes?
So I kind of actually had a question about that. So on the homework, there's an acid-base reaction between acetic acid
Right.
and the lumen on the acetic acid is the carbon oxygen star bond.
Okay, yeah, let's talk about this because I know this has caused some serious heartburn. And you're right to be worried about it. You were not meant to predict what the reaction would be here. You were meant to see what the reaction actually was and then retrospectively figure out what had happened. So the hard part is not the identification of the nucleophile, because you can see that this nitrogen has a lone pair on it, and you can see, that after the reaction, the nitrogen has a new bond to it. It's the electrons in this NH bond. And you can see that the hydrogen's over here. So it's a good bet that the nucleophile is this compound with the nitrogen on it, and that the HOMO is the lone pair on the nitrogen. The controversy comes when you decide that this is the electrophile. The molecule is actually called acetic acid. This is in vinegar. It tastes sour and tart. And when you look at this, if you were to follow the pattern for looking for LUMOs, important LUMOs, you would come up with, well, you want to pay attention to the carbon-oxygen pi star, but then you were also told to look for weak sigma stars, And so another possibility that you might not have been considering is the oxygen-hydrogen sigma star. The reason you want to consider it is because if you look at the reaction, what has actually happened here is that the nitrogen appears to have attacked the hydrogen and not the carbon. Can you see that? Because the new bond's with the hydrogen? All right. So you might have not been worrying about the oxygen-hydrogen sigma star, but the fact that the reaction gave you a new nitrogen-hydrogen bond sort of tells you what happened, right? It had to have attacked the hydrogen. Now I think the question is why, and how do you know that, and how can you predict it? I think what you're seeing here is sometimes in some molecules, there will be multiple empty antibonding orbitals that are competitive with each other in energy. So sometimes there will be multiple possibilities for a reaction, and this is one of those. This is maybe the only one I can think of at this point that would be useful for you to worry about. But to be clear, we're talking about two reactive places, the carbon of the carbon-oxygen pi star, and then the hydrogen of the oxygen-hydrogen sigma star. So if you're not sure how to predict what would have happened there, it's fine. You weren't meant to. That's why I gave you the result, and then you could understand and predict what had happened. The second thing that'll help you know what to do in this situation, and this is a carboxylic acid, and they're kind of unique. When you have a choice between removing a hydrogen and attacking a carbon, hydrogen is smaller, so it is sometimes easier to attack. It's easier for the nucleophile to get close to. We're going to deal with these challenges of multiple LUMOs or LUMOs in multiple places, sort of on a case-by-case basis, and I'll give you some tools for predicting what will happen here. Honestly, this kind of chemistry we're going to get to a little bit in chapter 2, but in terms of the issue of do you attack the hydrogen or do you attack the carbon, you'll see that that's a major issue in 352, and we'll talk about it more there. Any follow-up questions on that one? Go ahead.
So would the LUMO in this case be the sigma star?
A little bit louder, sorry.
Would the LUMO in this case be the sigma star?
The relevant LUMO that was involved in this reaction would be the sigma star. Yep, and you only know that because you're looking at the products. And so the mechanism for that reaction is nitrogen attacks hydrogen, and you break the oxygen-hydrogen bond. Yeah?
Is this mostly based on the mechanisms of like acid-base reactions, more or less, where a base attacks a proton? Is that why?
Sure, this is an example of an acid-base reaction where a base attacks a proton. And that's how all acid-base reactions function this way. Yep, good. Okay, I wanted to, go ahead.
Can you show us what it would look like if we were asked to draw the HOMO on the acetic acid? Is that non-binding orbital?
Yeah, so what would the HOMO on acetic acid look like? Well, here's a challenge. You've got two oxygens with two lone pairs. So it may be difficult to pick which is the most reactive lone pairs. I'm going to punt on that one because it's not going to be important until 352. The secret is resonance can give you a clue, but in general, if you were to draw a lone pair, what would it look like? Let's do that example. Look at and this is what Nate was explaining to you last week. If you looked at that oxygen, it doesn't make sense to really worry about hybridization on an atom that's only bonded to one thing, but if you did, you might be tempted to call this oxygen sp3 hybridized because it's surrounded by 4 groups. Does that make sense? So the lone pairs are each in sp3 orbitals, and if you wanted to draw one, you could just do this. Now, I don't usually bother because once you draw the lone pair, it's clear where the arrows start. But if you wanted to draw the HOMO on for a lone pair, you could draw an sp3 orbital, and it would look kind of like that. Yes?
The next question after this last one that we did on the problem set has a substitution reaction where the bromine just isn't shown. Is it like implied if it's
Oh, right. On the problem set, I think in the starting materials you have, it's a substitution reaction, so it's very much like this one that we just did. The only thing is I forgot to draw the Br minus that left.
Okay.
Yeah. Okay, the last one that I kind of wanted you to be aware of, and this is a challenging one, is an example of an elimination reaction. Sometimes reactions can happen between a HOMO and a LUMO in the same molecule on adjacent atoms. So a classic example of that might be this. Trying to decide what to do. Sure, that's fine. Let's just do this. Okay, so this is an intermediate in a reaction that you won't see until 352. There are multiple lone pairs in the molecule. If you had to choose which lone pair was highest in energy, you would probably choose the lone pairs on the negatively charged oxygen, because the chlorine doesn't have a negative charge. So you think the stuff with the negative charge on it is probably electron rich, and that's decent reasoning. If you were to look at the LUMO, the empty orbital in this molecule, of all the sigma bonds I have, I don't have any pi stars, I don't have any empty p orbitals. Of all the sigma bonds I have, the weakest is probably the carbon-chlorine sigma star. So if I were to draw that on this molecule, I'd draw little lobes pointing towards the node between the carbon and the chlorine, large lobes pointing away, and I can shade them like this to indicate the change in wave function sign, which is what makes this an anti-bonding orbital. Now, do you see how the negatively charged oxygen is adjacent to this sigma star? So actually, it's pretty easy for the lone pairs on that negatively charged oxygen to attack the sigma star. Now, normally when HOMO attacks LUMO, you get a new sigma bond. In this case, because there's already a sigma bond there, when HOMO attacks LUMO, we're going to get a new pi bond. And we'll see that this is general. When a lone pair attacks a sigma star on an adjacent atom, you form a new pi bond. Because you filled that sigma star, the chlorine must leave. You must break the bond. And the product is here. Here is the new pi bond that you made. It's the lone pair that did the attacking, and then the thing that had to leave because you were filling an anti-bonding orbital was Cl minus. Okay, that's called an elimination reaction. Yeah, go ahead.
This may be a silly question, but how do you determine on a molecule which is like the weakest bond or which is the basic?
Great question. How do you determine which is the weakest bond? So far, you only know because I told you, right? The chlorine, bonds between carbon and things that are much larger than carbon, like chlorine, bromine, and iodide, are generally longer, and longer bonds are weaker. So that's a clue. In chapter 2, we're going to talk about a lot of molecules like Cl minus, and we're going to see that atoms or molecules that are decently stable on their own with a negative charge often form weak bonds with carbon. You know, we've talked about chloro-leaving. I used that term in our discussion of this reaction. You break the sigma bond and chloro leaves. We're going to identify chloro as something called a leaving group because it is the group that left. Groundbreaking, right? We're going to talk about which kinds of groups are good leaving groups, and if you can identify good leaving groups are generally associated with weak sigma bonds. So that's going to be a key. All right, others? All right, well that is it. Yes, sorry, go ahead.
I was just gonna ask, so
Yes?
Is the halogen just content being off on its own? Like,
Yeah, great question. So you'll notice the charge stays the same in this reaction. Before it was on an oxygen, after it was on a chloro, the charge stays the same. So which way is sort of downhill? Is that kind of what you're asking?
yeah, I guess, like, is this reaction, like, actually favorable that happens?
Yeah, is this reaction favorable? The answer is yes, and I can actually give you a clue based on where we're going in chapter 2 about why. Okay? So, stay with me. One major principle in OChem is you can tell how stable something is with a negative charge by assessing how acidic its conjugate acid would be. That seems convoluted. Do you guys know what a conjugate acid is? Okay. Conjugate acid is what? You add a proton where the negative charge is, right? Or where the lone pair is. So if I were to look, so just stay with me here. If I were to look at the conjugate acid of a negatively charged oxygen, what would that be? What should I add? A hydrogen, right? So this is now the acid, this is now the conjugate acid of this base. Everybody okay with that terminology? Okay. How about Cl minus? We'll talk, Cl minus is a base, not a very good one. What is the conjugate acid? HCl. Okay, now, it turns out that the strongest conjugate acid has the corresponding base that is happiest with a negative charge, happiest with extra electron density, most stable. In general, you will see as a principle in OChem, strong acids are strong. So far, that sentence is really not informative. Strong acids are strong because their conjugate bases are very stable. And if you want to anthropomorphize your molecules, which I'm not a huge fan of, you can say they are happy with a negative charge, or alternatively, extra electron density. So, one of the ways we assess the strength of an acid is by a number called pKa, and I will show you where that number comes from, help you understand what it means. But for right now, pKa is a measure of acid strength. Have I lost some of you in post-106 PTSD? You hear pKa, you're like, I never wanted to hear that again. Don't worry, the bad man is gone. pKa is going to be your friend in 351. pKa is a measure of acid strength, and the lower the pKa, the stronger the acid. And I'll show you why that is. All right, so let's just look at it here. I happen to know that the pKa of the conjugate acid of that negatively charged oxygen is 16. I happen to know that the pKa of HCl is -7. So, which acid is stronger? HCl, stronger acid. And actually, it's not just stronger by, 23. It's stronger by 23 orders of magnitude. pKa is log units. So HCl is 10 to the 23 times, that's a 1 followed by 23 zeros, more acidic than the alcohol. Okay? So that's massively, that's like we don't even have a word for that number. That's why we go to scientific notation. So what that tells you is Cl minus is way more stable than the negatively charged oxygen, which I'm abbreviating there as RO minus. Do you follow that reasoning? HCl is a stronger acid than the alcohol, the ROH. Therefore, the conjugate base of HCl is way more stable than the conjugate base of ROH. That's really super key, useful reasoning that we're going to use as we talk about acid-base chemistry. And we're going to be using it to develop some intuition about which reactions are favorable and which groups are better at leaving than others. Yeah?
So would it be safe to say that the conjugate base of strong acids are generally going to be a leading group because they're going to be more stable?
Yep. So leaving groups are generally going to be, good leaving groups are generally going to be conjugate bases of strong acids. Excellent. So that's one of these key principles you want to write down and take to the bank. Good leaving groups are conjugate bases of strong acids, always. So if you can, this is why the stuff in chapter 2 about pKa matters. We're less worried about making buffers that have the right pH. I mean, that's a useful skill, but we don't care that much in this class. Instead, we're going to use pKa information to help us predict the way reactions go. All right, so get ready because I need to show you where pKa comes from. Most of you are prepared to accept it on faith, but I like seeing the math. So this is somewhat self-indulgent, but it's my class. All right, here's where pKa comes from. You have an acid, HA. Oops. And you react that acid with water. Now, here's where we're going to reveal something to you that you thought was a certain way and it's not. You guys ever remember learning about acid dissociation? Oh, the acid loses its proton, and you imagine that the proton went floating off as H plus somewhere into the universe. Not actually what happens. You know this now because what has to happen is the HOMO from water, H2O, attacks the LUMO of the acid, the HA sigma star, and the bond breaks. And that gives you H3O plus, and that gives you A with the lone pair on it, A minus. All right? So that's one thing that you need to sort of correct in your understanding of acid-base chemistry from Gen Chem. Protons do not float off into the ether, wherever that is. They are removed by bases. And we assess acid strength by comparing the strength of this acid HA to the strength of this acid H3O plus or hydronium. This is an equilibrium, and there is an equilibrium constant here. Just to have a few definitions, HA is the acid, here water is the base, A minus is the conjugate base of the acid, and then H3O plus is the conjugate acid of the base. Notice that conjugate acid and conjugate base are relative terms. You're a conjugate base of something. It's asking whether something is a conjugate base is like asking someone whether they are a cousin. It's like, I mean, of who? Of whom grammarians out there, right? So anyway, it doesn't make any sense to ask, is that a conjugate base? No, it's always, is that the conjugate base of this? So to show you where pKa comes from, let's just write out the equilibrium expression, the expression for the equilibrium constant here. KEQ should equal the concentration of A minus. It's really not going to be that long, so just endure it. HA here, and then the concentration of water. That's the equilibrium expression. Now, it turns out you can, because the concentration of water is like 55 molar in an aqueous solution, it doesn't change much as the reaction proceeds. So we're going to go ahead and multiply both sides of the equation by the concentration of water, or in other words, move the concentration of water over to the other side of the equation because it's basically constant. And then that gives us, that is our new Ka, our acid dissociation constant. You've probably seen this before. When you saw it before, probably this was H+, but we're dispensing with the fiction that H+ exists in water. It doesn't. It's always H3O+. All right? So then we get pKa by taking the minus log of Ka. Why is it the minus and why is it the log? First, we take the log because Ka varies over massive orders of magnitude. It varies from 10 to the minus 10 all the way up to 10 to the 40. And we get sick of writing superscripts on the number 10. So to get rid of that, we just use the logarithm. We deal with powers of 10. So you take the minus log of both sides. Now, this is painful, but you'll have to maybe remember, or at least trust that I remember, properties of logarithms and some things you can do with products within logarithms. But we could say that pKa equals the minus log of H3O plus minus the log of A minus divided by HA. That's just properties of logarithms, and if you don't remember, that's okay. Turns out, though, you've seen this before. The minus log of H3O plus concentration is simply pH. And then to avoid negativeness, which sometimes stresses me out, actually, I'm going to leave it. I think that's fine. Sorry. You can play around with the plus or minus in the log as much as you want, but we'll just leave it like this. So this is an equation that's actually called the Henderson-Hasselbalch equation. We're going to come back to it, but this is where pKa comes from. And I want you just to remember, just have in your mind right now, that there's a relationship between pKa and pH that will tell you about how much of a conjugate base versus its acid you have present at equilibrium. We'll come back to that. But that is the definition of pKa. And as I said above, pKa, if it's lower, the acid is stronger. Okay? When pKa is lower, the acid is stronger. Okay, questions? Yeah. Will we need to calculate pKa? No, absolutely not. You will need to be able to use a table of pKa values, along with a couple that I'll ask you to memorize, but there's going to be no, if you can do greater than, less than, you're probably okay. Yep. All right. So let's talk about some acids and start rationalizing, looking at some pKa data, describing which acids are stronger, and then making some judgment calls. So here I'm going to list some various acids, and I'm going to list their pKa values, and then we need to rank them in order of acidity, and then we want to actually explain why. So this is HI. Its pKa is actually minus 11. This is HF. Its pKa is 4. This is H3O plus, which I can draw like this to indicate that we're worried about this OH bond. Its pKa is minus 2. I do want you to memorize this pKa for hydronium, but you don't have to memorize the other pKa's on this list. Let's draw, what else? I'm not giving you a comprehensive list of pKa's. Let's draw HBr, which has a pKa of minus 9, HCl, which has a pKa of minus 7. So if we want to put these in a list from most acidic to least acidic, who's on the top of the list? HI, I actually put it on the top of the list, so that's kind of a dumb question. All right, who's next? All right, good, and you know that because the lower the pKa, the stronger the acid. So HBr should be there. Who's next? HCl, okay. And then who? Hydronium, and then HF. Good, that is the rank of most acidic to, and acidity is relative, so less acidic relative to the stuff that's more acidic. Now for a moment, I'm going to take hydronium off this list because it's not exactly a fair comparison, because oxygen's from a different column of the periodic table than HF. And I want us to consider why acidity follows this trend with these halogen acids. Because it's somewhat backwards from what you might think. The easiest thing to worry about when thinking about trends is electronegativity, right? You recognize that fluorine is most electronegative and that iodide is least electronegative in this list. And if all you're used to thinking about is electronegativity, you might say, oh, well, shouldn't the HF bond be weaker because it's polarized more towards the hydrogen? It turns out that's exactly wrong. So let's talk about how you can rationalize acidity and get the right answer. The best thing to do when trying to rationalize acidity is to consider the stability of the conjugate base. So we're going to draw the conjugate base for each of these acids. It's I minus, it's Br minus, it's Cl minus, and it's F minus. So when discussing how acidic groups are, we want to ask, how good are their conjugate bases at stabilizing a negative charge? Okay. Now again, you've got one trend which says that F minus is most electronegative and I minus is least electronegative. And that would lead you to believe that fluorine is best at accommodating a negative charge. But electronegativity is only part of the picture. We're going to see that there are multiple ways, and I can't spell accommodation to save my life, so I think there's two N's, M's. It's not even an N in that molecule, accommodating a negative charge. There's multiple ways to doing it. One is to be electronegative, and two is to spread out the charge, that is delocalization, through space. And you can do delocalization either by having the atom that holds the negative charge be large, or you can have resonance stabilization. Now in the case of the halides, there's no resonance stabilization, but you may have learned that iodide is large and fluorine is small. Iodide spreads out electron density through a larger area of space than fluoride does. Fluoride is very small. And spreading out electron density through space is stabilizing. You can accept that on faith. I told you that electron delocalization is stabilizing. Or if you want, you can come and we can talk about second derivatives in my office, which I know nobody wants to do, right? So being large, having an atom on having a negative charge on an atom that is large is one of the ways you can be stable, and it turns out that is going to be more important than electronegativity when there is a size difference. So we will see that I minus is most stable. Okay, we got some more to do on chapter 2. We'll be on that next time on Wednesday, so I will see you then. Have a good day.